All right, let's talk about quantum computers. We've all heard the hype, right? But do we really know where their incredible power actually comes from? Today, we're going to bust one of the biggest myths out there about quantum speedup and get to the truth of what's really going on. I'm willing to bet you've heard some version of this, right? It's a really popular idea. And honestly, it's pretty seductive. The thought of a quantum computer as this magical machine with a bajillion parallel processors, checking every single possible answer all at the same time. It sounds amazing. And it kind of makes sense on the surface. But what if that simple, super appealing idea isn't just wrong, but is actually holding us back from understanding how quantum speedup really works? Well, that's exactly what we're going to dig into today. So this idea, this parallel universe, or try everything at once concept, it's a really common myth. And look, I get it. It's an easy way to wrap your head around quantum computing. The problem is it leads to some wildly wrong ideas about just how fast these machines are. So let's get specific and see exactly why that is. Okay, let's make this concrete with a classic problem. Let's forget all the abstract theory for a second. I want you to imagine we're on let's call it a quantum search party. Our mission is to find one specific piece of info that's buried in an absolutely massive pile of data. So here's our setup. We've got this gigantic, totally unsorted database. You can think of it like a black box function. We know there's one single needle in the haystack, one magic input, let's call it S, that gives us the answer we want. Every other input, a dead end. Now, with a regular computer, the only way you can find S is, well, to just start testing inputs one by one. With a classical computer, the strategy is pretty straightforward, right? It's just guess and check. If you have, say, n items in your database, on average, you're going to have to check about half of them to find the right one. In computer science lingo, we call this linear scaling, or big O of n. Basically, a list that's 10 times bigger is going to take you about 10 times longer to search. Okay, now for the fun part. If you were still holding on to that myth, the one where a quantum computer tries all answers at once, which one of these would you pick? Be honest. I'm guessing most people would immediately jump to A or B. I mean, it should be instantaneous, right? But they'd be totally wrong. The real answer is, well, it's a bit more subtle than that. And frankly, it's way more interesting. It really gets to the core of what makes quantum computing so powerful. The correct answer is C. The runtime for a quantum search is on the order of the square root of n. And this isn't just some random guess. It's a mathematically proven optimal limit for this exact kind of search. It's achieved by an algorithm called Grover's algorithm. It's not magic, it's just incredibly clever math. Now, this is where it gets really cool. This table shows you that even though it's not instant, the speedup is still mind-blowing. Let's put this in perspective. To search 1 million items, a classical computer needs, on average, 500,000 tries. A quantum computer, it needs about 1,000. Now scale that up. For 1 trillion items, a classical machine needs 500 trillion operations. The quantum computer, just 1 million. That isn't just a little faster. That's a world-changing, game-changing speedup. So the big question is, if it's not checking all the answers at once, how in the world does it pull this off? To get our heads around this square root speedup, we basically have to toss out that old mental model. We need to replace it with something new, something based on the bizarre but incredibly powerful rules of quantum mechanics. Okay, this right here is the most crucial point. When you run a quantum algorithm, you do not get a big long list of all the possible answers. Instead, the machine gives you just one single answer, and that answer is randomly sampled from a probability distribution that the algorithm has been carefully cooking up. You never ever get to peek behind the curtain and see all those parallel universes at once. So what's the engine that builds this special probability distribution? Well, it's not actually based on probabilities themselves, but on something much, much weirder, something called amplitudes. You can think of amplitudes as these hidden numbers that are secretly describing the quantum state. Now, probabilities, the things we actually measure, are always positive, right? They go from 0 to 1. But amplitudes, they can be positive or negative, just like the peaks and troughs of a wave. And trust me, that little difference changes absolutely everything. So how do we get from this hidden world of amplitudes to the real world of things we can actually measure? It's all connected by a surprisingly simple but really powerful formula called the Born rule. It just says this: the probability of measuring any specific outcome is just its amplitude squared. That's it. So a small amplitude means a low chance. A big amplitude means a high chance. The entire game of quantum algorithms is just figuring out clever ways to manipulate these amplitudes. All right, so now we have the pieces. Let's see how they all come together in the clever algorithm that actually achieves that square root speedup. you'll see it's less about brute force and a lot more like a beautiful, intricate geometric dance. And this is really the fundamental trade-off, the big catch of quantum computing. Yeah, the internal state can hold a huge amount of information in all those amplitudes. But, and this is a big but, you can't just read it out directly. It's all locked away. The only way to get any information out is to become a master choreographer, carefully directing how those amplitudes evolve so that when you finally take that one measurement, the answer you want is the one that's most likely to pop out. Grover's algorithm is an absolute masterclass in this kind of choreography. At its heart, it's a simple two-step dance that just gets repeated over and over. First, a special piece of the algorithm called an oracle goes in, finds the right answer, and instead of telling us what it is, it just flips the sign of its amplitude from positive to negative. Then, a second step, called a diffusion step, comes in and cleverly magnifies that tiny little change, basically pulling all the other amplitudes towards the one that just got flipped. And that right there is the core idea. Every time you run that two-step loop, it's like performing a small geometric rotation. You're just nudging the whole quantum state a tiny bit closer to the correct answer. You do this about the square root of n times, and by the end, the state is pointing almost directly at the solution. The amplitude of the correct answer is now massive, and all the other wrong answers have their amplitudes shrunk down to practically zero. So after all that, we can finally come back and answer our original question. Where does this incredible power really come from? The secret sauce isn't parallelism, it's interference. Because amplitudes can be negative, they can cancel each other out, just like when two waves meet. We call this destructive interference. The wrong answers are literally engineered to cancel each other out into nothingness. At the same time, the pathway to the right answer is amplified through constructive interference. The algorithm is so clever because it gets all the wrong answers to basically silence each other, which makes the right answer ring out loud and clear. So let's just throw out that old, broken myth and replace it with a new, much more accurate cheat sheet. Here's what you need to remember. 1. Quantum computers give you one single sampled answer. 2. Their real power is hidden in their amplitudes. 3. Probability is just that amplitude squared. 4. The advantage comes from clever interference, not brute force parallelism. And finally, 5. Grover's search gives us a powerful, but not instant, square root speedup. This is the real foundation of how quantum computers work. And that really leaves us with a fascinating final thought, doesn't it? We've just seen how a problem that looks like it needs pure brute force can actually be solved with a clever geometric trick in this weird abstract space. It really makes you wonder, what other impossibly hard problems are out there, just waiting for someone to find the right quantum insight to crack them wide open? Thanks for watching. Reality X Decoded isn't official teaching. We simply explore and aim to stay as accurate as possible. If anything seems off or you have questions, comment below and let us know what to decode next. Don't forget to subscribe.